When we use the Measure tool in ArcGIS Pro, we notice there are a number of measuring options. In this video, we'll look at what they are and why they exist. We can see the behavior of the measuring tool changes with the different options. For example, if we use the geodesic option, we can see the line bends when we measure between New York and Milan. If we use the planar option, we get a straight line and a very different distance. So what is going on here? Well, a geodesic line is the shortest distance between 2 points. This particular map is using the default Web Mercator projection. This projection is a conformal map projection and does not represent distances accurately. Therefore, a straight line on the map is not necessarily the shortest path between 2 points. The tool is therefore taking into consideration the curvature of the Earth and showing us the actual path of the shortest distance and what that distance is between the points. On the other hand, the planar measurement is giving us the straight line distance on this particular projection. And the planar distance may change when the projection is changed, as different projections have different properties. The geodesic option might make the path appear to be different in a different projection, but the distance should always be the same, as it is just showing us the shortest distance between the points. So the geodesic and planar distances are only likely to be similar when looking at a small area, like a city or county. And indeed, the planar option should only be used for measuring within a small area. Let's consider some of the theory behind this. On the Earth, how do we know what the shortest path between 2 points is? Here we can introduce the concept of great circles. A great circle divides the Earth into 2 equal parts. The equator and all lines of longitude are great circles. If we create a great circle anywhere on the Earth that runs through 2 points, we will get the shortest path between those points. This explains why when we measure along the equator and the lines of longitude using the geodesic option, the tool follows those lines. These lines are great circles, and therefore any points along these lines are the shortest path. When we move away from those lines, we can see the shortest path is curved in this particular projection. Technically, a great circle is the shortest path on a sphere, and the Earth is a spheroid. That is, it is slightly fatter around its middle, but it's very close to being a sphere, so great circles are often used to calculate the shortest distance on the Earth. So what about the other option, loxodromic? Here the measuring tool gives us a relatively straight line between New York and Milan, but the actual distance is more than the geodesic distance. A loxodrome, also called a rhumb line, is a path that crosses all lines of longitude at the same angle. This gives us a line of constant compass bearing. On this projection, that line will be straight. That is because this projection is a derivative of the Mercator projection. If we look at the historical context, the Mercator projection was specifically designed to address the challenges faced by navigators of the era. As a result, straight lines drawn on the Mercator map represents constant compass bearings on the Earth's surface. The captain of a ship could draw a straight line to a destination on a Mercator map and then follow this compass bearing to arrive at the desired destination. This straight line would not necessarily be the shortest route, as we've seen, but by being able to simply follow a constant compass bearing, this greatly simplified navigation. If we change the projection to the Albers equal area projection, we see the loxodromic line between New York and Milan is no longer straight. This is because the Albers equal area projection has very different properties to the Web Mercator projection, and the properties of loxodromes or rhumb lines are no longer preserved. So the measuring tool when using the loxodromic setting is showing us the path and distance between 2 points if we follow a constant compass bearing. The final option in the measuring tool is a great elliptic. A great ellipse distance is very similar to a great circle distance. It is sometimes used in navigation and will produce a very similar distance to a geodesic distance. However, for most users, the geodesic setting, the shortest path between 2 points, is likely the option that will be appropriate for most users. The complexity in measuring on maps is all the consequence of representing our three-dimensional Earth on a two-dimensional map. And if you'd like to learn more about projections and coordinate systems, take a look at the Spatial Monkey online course. In it, we go through all the different types of projections and the properties they hold, how to select the right projection, and make sure we avoid any location errors, something all of us map makers strive for. Check out the link in the description.